Hi, in this video we are going to talk about multiple reactions in series. Uh, for irreversible reactions considered in a series configuration like A gives R gives S, the mixing of fluid for the different composition is the main controlling factor for the formation of the intermediate. Okay, and the maximum possible amount of any of the intermediate, in this case being R, is obtained if the fluids of different compositions or the reactants of different compositions and at different stages of conversion are not allowed to mix. Okay, so here we are just going to see reactions in series for the irreversible type, and for different kinds of reactors, what would be the way we quantify the product distribution and the reactor sizing. That is the target over here. So we are first considering this reaction configuration for plug flow reactor or batch reactor. Okay, and let me write the rate constant. So K2, K1 for the first reaction and K2 for the next part after the formation of the intermediate. Now in this case we are replacing the reaction time by space time. Okay, and we can get the following set of equations: Ca by Ca naught equals to e to the power minus k1 tau, where tau is the space time. Cr by Ca naught is obtained as k1 by k2 minus k1 multiplied by e to the power minus k1 tau minus e to the power minus k2 tau. Cs can be written as Ca0 minus Ca minus Cr. So accordingly you can just plug in the values that you obtain. The maximum concentration of intermediate, that is Cr max, is obtained as Ca0 multiplied by K1 by K2 to the power K2 by K2 minus K1. Okay, this is Cr max. And tau p optimum, the optimum space-time requirement for the plug flow reactor, is given as 1 by k log mean, and this log mean k uh, sorry log mean k is given as k2 minus k1 by natural logarithm of k2 by k1. Okay, uh, this point, this tau p optimum is also the point at which rate of formation of S is most rapid. Okay, rate of formation of S is most rapid. This is for plug flow reactor or batch reactor. If we consider for the same set of equations, A gives R gives S, for a mixed flow reactor, then Ca by Ca naught is given as 1 by 1 plus K1 tau m. So m being for the mixed flow reactor, then Cr by Ca naught equals to K1 tau m by 1 plus K1 tau m multiplied by 1 plus K2 tau m. Okay. Now Ca plus Cr plus Cs, this will be constant for the mixed flow reactor, and this is equals to Ca0. So you can use this and get that Cs by Ca naught equals to K1 K2 tau m square by 1 plus K1 tau m multiplied by 1 plus K2 tau m. Okay, this is how you will be obtaining. To get the maximum concentration for R, that is Cr max, you need to obtain the stationary point for dCr by d tau m. So if you set dCr by d tau m equals to 0, then you will get the uh, maximum concentration of R. Okay. Also, you will obtain the final expression as Cr max by Ca naught equals to 1 by K2 by K1 to the power half plus 1, and this has been whole squared. From the same expression you can also get tau m optimum, that is the optimum spacetime for the mixed flow reactor, is 1 by root of K1 K2. Now you may feel that I'm just writing the equations and just the final formulation. Actually these derivations are all from the reaction type and the rate equations, using the general approach to treat multiple reactions. But for the interest from the examination perspective, it is better that we get hold of the formulas at first and we practice those. So I am just enlisting the formula for series reaction. Now let us take one special case. So I am considering first order reaction followed by zero order reaction. Okay. So A gives R gives S. K1 and K2 are the two respective rate constants, and for the first reaction the order is 1, and for the second reaction the order is 0. So if I write the rate expressions, it will be something like minus Ra equals to K1 Ca and R equals to K1 Ca minus K2, because the second reaction is zeroth order, so it is independent of the concentration. And we are also writing a term capital K as K2 by Ca naught by K1. Okay. Now if you will write the expressions for these kind of reactions, then considering a batch reactor or plug flow reactor, Cr0 equals to Cs0 equals to 0, that is at initial. That is pretty much clear. You only have the reactant A over there. Then Ca by Ca naught equals to e to the power minus K1T. Here T is the reaction time. Okay. And Cr by Ca naught equals to 1 minus e to the power minus K1T minus K2 by Ca naught T. Okay. The maximum concentration of the intermediate, that is Cr max, is obtained as Ca naught multiplied by 1 minus capital K, which was equal to K2 by Ca naught by K1, multiplied by 1 minus natural logarithm of capital K, and Tr max, that is the time where the maximum concentration of intermediate occurs, that is 1 by K1 multiplied by natural logarithm of 1 by capital K. Okay, these are the mathematical you know uh, formulations to treat first order reactions followed by zero order reaction in series. Another case is where zero order reaction is followed by first order reaction. Okay, so in this case, A gives R gives S at the respective rate constants K1 and K2, where the order of the first reaction is 0 and second reaction is 1. Okay, in this case, minus Ra equals to K1 and Rr equals to K1 minus K2 Cr if A is present, else it is minus K2 Cr if A is absent. Okay, so these are the two cases because the first reaction is now a zeroth order one, that is independent of concentration of A. Okay, and accordingly you can write the term capital K as K2 by K1 by Ca naught. Okay, so for a PFR or a batch reactor with initially no R and S present, that is Cr naught equals to Cs naught equals to 0, we get Ca by Ca naught equals to 1 minus K1T by Ca naught. Okay, now again for Cr by Ca naught, we have two expressions. First is 1 by K, capital K over here, multiplied by 1 minus e to the power minus K2T when T is less than Ca naught by K1, and the other expression is 1 by capital K multiplied by e to the power K minus K2T minus e to the power minus K2T. This is for T greater than Ca naught by K1. Also, if you want to find the maximum concentration of intermediate, that is Cr max, that is equals to 1 minus e to the power minus capital K by K, and the corresponding time, that is Tr max equals to Ca0 by K1. Okay, so if you want to find the concentration of R uh, when the maximum is not reached, that is it passes through a maximum point and then again drops. So if you are at this point, then this time corresponds to Ca0 by K1 on a plot of Tr and Ca0. I mean, sorry, I should write Ca over here. So this point corresponds to Ca naught by K1, where Tr max is obtained. and below that or above that, to find the concentration of R in the system, you have to use these expressions. Now there are also other kinds of systems where you have successive irreversible reactions of various orders. So in that case you have to use the concentration time plot, and then you have to obtain, and you have to employ numerical methods. So we have discussed the simplest case. Also the same thing persists for reversible reactions, that you have to do a detailed analysis of the concentration time curves. With this, we come to the end of our discussion on multiple reactions in series. Thank you.